Today's lesson is lesson 3.1, which is all about complex numbers. And before we get into complex numbers, I just kind of want to review the real number system, which is the box on the left side that has the yellow and everything in between it. So the real numbers, starting from the most specific set of real numbers, so in the middle, the counting numbers. The counting numbers are kind of what they sound like. If I were to start counting, I'd say 1, 2, 3. Those are the counting numbers. So it starts at 1 and then goes 2, 3, and so on. And when like a set is going to continue going forward, we use the dot 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 to show that it keeps going on forever. And then usually we write number sets with this kind of funky like bracket that has a little curve next to it. If you're having a hard time drawing that, feel free to just use a regular bracket. And then the next set is whole numbers, which is very similar to counting numbers. It just has one extra number, which is 0. So instead of starting at 1, it starts at 0 and then goes 1, 2, 3, and so on, goes on forever. And then you can see there's some overlap, and that's why the diagrams can be arranged like this, because technically all counting numbers are also whole numbers, and that means like all whole numbers will also be integers, and so on up the list. One thing I want to add is for counting numbers, there is another word sometimes used to describe it. I think I only saw counting numbers in your workbooks, but the word natural, so natural numbers, also means the same exact thing. And then the next one is integers, which is similar to whole numbers, except for we include all of the negative versions of each number. So it would be 0, 1, 2, and so on. It would keep going up, and then it would also be the negative version, so -1, -2, and so on. And since that keeps going down forever from -2, like we could do -3 and -4, we use the dot 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 on that side as well. And then rational numbers are numbers that can be written as a fraction. So like kind of your obvious fraction like 1/2, or it could be a negative as well, like say -5/4. It could be an improper fraction like that. It could technically be a mixed number if you wanted to, but we don't see mixed numbers as much at this level of math. It can technically also be certain decimals. So it can be decimals that end or repeat. So it could be like 0.6, because that can be written as a fraction, right? It's 6/10. Or it can be any decimal that repeats, so like 0.3 repeated. That can technically also be written as a fraction. It's 1/3, and that's the case for all repeating decimals. They can all be written as a fraction. So those are just some examples for the like types of decimals that don't end and don't repeat. Those are called irrational numbers. Probably the most like common example of an irrational number would be pi. So down here you'll notice like irrational numbers is kind of its own separate thing, because it doesn't have any overlap with the other numbers other than just the whole real number system. So for pi, remember pi is like 3.1415, and so on, continues forever, and it doesn't repeat. So you can't write it as a decimal, it's impossible, or sorry, as a fraction, it's impossible. There's some other examples too, but I think pi is the most common one that we use. Okay, and then the real numbers just include all of that. And then there is, I guess, opposed to, that's not the right word, but there's real numbers and imaginary numbers, which imaginary numbers kind of have this imaginary unit called I that we'll talk about in a second. And then there's complex numbers, which combine real numbers and imaginary numbers. So real numbers is what you work with most of the time in math. Today we're going to incorporate imaginary numbers, and complex numbers is the combination of the two. Okay, so moving down to imaginary numbers in the imaginary unit. So let's say I wanted to take the square root of a -1. So I know that if I were, and you don't need to write this next part, if I were to take the square root of 1, that would be 1, since if I were to square 1, it would get me back. But let's say I wanted to square -1. If I did -1 squared, that would still be +1. So there's basically no number that I can square that would make it equal -1 or any negative in general. So that's where the imaginary unit comes in. Because we can't take a number, a real number, and square it to get a negative number. So instead of a real number, we'll use an imaginary number. So the square root of -1 is technically our imaginary unit I. And when you write it, I would try to draw like the little kind of like loopy I, so it doesn't get confused with a 1 or anything else, but just kind of give it a little bit of a distinction. But that's our imaginary unit, and it comes from taking the square root of -1. So example over here, sorry, the square root of -4, we would treat it like any other square root problem. So like if I were to take the square root of just 4, that would be 2. But because I'm taking the square root of a negative, I have to incorporate the I. And we're not solving here, so I'm not going to put the plus or minus. You could, it would not be incorrect if you put the plus or minus out in front. But usually we just kind of do that when we're solving for x. Another way of like kind of approaching this problem is as if you were simplifying a radical. So I could break this down into its factors. I could say this is the square root of 4 and then times the square root of -1, which the square root of 4 is 2 and the square root of -1 is I. So that way works as well. But just know anytime you're taking the square root of a negative in any capacity, you're going to end up pulling an I out of the radical. Okay, the next section is complex numbers, which is the combination of real numbers and imaginary numbers. So if we go back up here, you can see complex numbers is like the huge blue box that holds both the real numbers and the imaginary numbers. So complex numbers, they have a real part and an imaginary part. And then when they're written in standard form, they are A plus B I. So this is standard form. And that would be the order that you would be expected to write your complex answers in. So the real part is just the part that doesn't have I. And then the imaginary part is the part that does have I. So this is my real part, no I involved, and then this is my imaginary with the I involved. So the next example over here to the right says identify the real part and the imaginary part of the complex number. So for the real part, just the part that doesn't have the I attached to it, so the 7. And then the imaginary part is the part that does have the I, so the 4. So this is my real, the 7, and then this is my imaginary, the 4I. So the next example, number 1, it says write the following complex numbers in standard form, which like you may look at 7 and be like, okay, well 7's not a complex number. It's just like pretty much a regular number. It's technically a natural number or a counting number. But if we go all the way up here, so 7 would be like our most specific like type, this counting number set. But that counting number set is still within the whole complex number system. So even though it's pretty simple, it's still within that and we can still write it as a complex number. So the 7 does not have like an I attached to it, so that would be considered our real part. So I'm going to write that part first because real always goes first, so do 7. And then because there's nothing added to it, that actually just means our imaginary part is 0, so we would write it as plus 0I. So this is my real part, this is my imaginary part. I didn't like really change the value in writing it like that because I was just adding 0 and that doesn't change anything. I just wrote it as standard form for a complex number, so my A plus BI. And then now on to number 2. So 3 plus the square root of -25, I just want to make sure that I simplify it first if I can. So for 3, I'm just going to bring that down, and then for the square root of -25, I know the square root of 25 is 5. And then because it's negative, I also have to include an I. So if I take the square root of 25, it's 5. If I take the square root of negative, it's I. And then this is already in the correct order, so I'm technically done here. So it's the real part, my like A, and then plus my imaginary part BI, and I don't have to do any reordering or anything like that. And we can't simplify it any further, like I couldn't add these two together because think of it as like they're not like terms, so I couldn't add real parts and imaginary parts. Okay, then next one, number 3, the square root of negative 72 minus 4. We need to simplify this radical, so 72 is not a perfect square. So it does have perfect square factors though. So I'm going to go ahead and simplify it. I'm going to make a factor tree for it. That's usually the way I use it, or sorry, that's usually the way that I simplify radicals, just because the other way is faster if you can think of the factors quickly. But the factor tree works, I would say, more consistently across the board. But I'll show you both ways. I'll show you the second way after. Okay, so 72, and we're not going to worry about the negative for right now, but 72 I know is 8 times 9, and then 8 I know I can do 2 times 4, and then 4 I can do 2 times 2, and then 9 I can do 3 times 3. So when I'm taking square roots, I'm looking for pairs of the same number. So I have a pair of 2's, and then I have a pair of 3's, so that means that I could pull out a 2 and a 3, and I would multiply those together to get 6. And then because I'm taking the square root of a negative, I'm also going to pull out an I, and then I have my radical, and I have this leftover 2 over here that's not a part of a pair, so it'll have to stay inside, and then I would bring down my minus 4. Okay, so one more time I had a pair of 2's and a pair of 3's, so I could pull out a 6 because I would pull out a 2 and a 3 and multiply those together. And then it was negative inside the radical, so I pulled out an I, and then this 2 was left over. It wasn't part of a pair, so that stayed inside the radical. And then now I just need to make sure that I rewrite this in standard form, which has the real part coming first. The real part is the part that does not have the I, so it would be negative 4 in this case. And then the imaginary part is the part that involves the I. So I just kind of have to switch the order. So I'll bump that up to the front. So it'll be negative 4, the negative belongs with it, and then plus 6i root 2. And then, of course, my negative 4 is the real part, my a, and then the 6i root 2 is my imaginary part, it's bi. And then the other way of simplifying the radical is if you kind of were to recognize really quickly that 36 is a perfect square and it's also a factor of 72, you could rewrite this as the square root of negative 36 and then times the square root of 2. And then the square root of negative 36 would be 6i, and then the 2 stays inside the radical. So really whatever you prefer, and it could change depending on the problem. Okay, the next section is 3.2. It's complex solutions in 2 different ways. So first by square roots, and then second by completing the square. And then the last section, which this is a typo down here, it should say 3.3, is complex solutions with the quadratic formula. So kind of all of our methods of solving besides factoring, I guess, and graphing, which we don't really use as much. So 3.2, I'm going to start with complex solutions by square roots, which solving by square roots is essentially trying to get x by itself. So I'm going to start isolating it. So the first thing I'm going to cancel out is I have this plus 25. So in order to cancel that out, I'm going to subtract 25 from both sides. And then I'll bring down my 49x squared. These cancel out, and then I have 0 minus 25 is negative 25. And then still working towards getting the x by itself, so I'm going to divide both sides by 49. And then 49 divided by 49 is 1, so that clears out. And then I have x squared equals negative 25 over 49. You want to leave it as a fraction, so it'll be easier to take the square root of that way. And then I want to try to get x completely by itself, so to cancel out that power, I'm going to square root both sides. That gets rid of my power and I'm left with just x. And then in this case, I'm solving. So I want to include the positive and the negative version. So it'll be plus or minus. Even when it's like you're taking the square root of negative, you still put the plus or minus out in front. And I'll do the numerator first. So for the square root of negative 25, it would be 5i. And then for the denominator next, it would be the square root of 49, so 7. So my final solution is x equals positive or negative 5i over 7, which if you remember from when you first learned how to graph quadratics, the solutions ended up being the x-intercepts. So we got a solution here, but it was an imaginary. So that means we have imaginary x-intercepts essentially. So this graph on the right is the graph that goes along with this equation. It would technically be like f of x equals 49x squared plus 25, but you can see there's no x-intercepts, and that's because we had a solution that involved I. We had an imaginary solution. We'll talk about that more after this next example. Okay, the next example is complex solutions by completing the square. So in lesson 2, we went over completing the square in a lot more detail. So if you need more examples of that, I would go back to lesson 2. It gives like kind of written examples of each step. So the first step is to divide everything by the lead coefficient, but the lead coefficient in this case is 1. So we don't need to do that step because it's already done for us, or it just wouldn't make a difference in the equation. Next, I want to isolate the parts that involve x. So I have x squared plus 8x. I want to get those by themselves. So I need to cancel out this 20. So it's a plus 20. I'm going to subtract 20 from both sides. I bring down the x squared plus 8x. And then I have 0 minus 20 is negative 20. And then next I need to find b over 2 squared, which b is the coefficient of x, so in this case b is 8. So I would find 8 over 2 squared, which 8 over 2 is 4, and then I have to square that to get 16. So my b over 2 squared turned into 16. I have to add that to both sides of the equation, once after the 8x and then after the negative 20. So we add it to the left side, x squared plus 8x plus 16 to create that perfect square trinomial so that we can factor it. And then we have to add it to the right side in order to make sure that we're keeping the equation balanced so that we're not changing the overall solution. So it would be negative 20 plus 16. And then now on the left side, I have a perfect square trinomial, so I can factor that, and we can factor it using a pattern. So it always factors into a binomial squared. And then the pattern is we take the square root of the first term, so the square root of x squared is x. And then we take the sign from the middle term, so plus, if it was a minus, we'd do minus. And then the square root of the third term, which the square root of 16 is 4. And then is equal to negative 20 plus 16, which is negative 4. And then now we're ready to square root both sides to get rid of that power and free up the x plus 4. So square root both sides. That cancels out my power, so I'm left with just x plus 4. And then remember, we are solving, so when we take the square root of something, we have to include the plus or minus. So this would be positive or negative. The square root of negative 4 would be 2i. So 2 from the square root of 4, and then I from the square root of the negative. And then my ultimate goal is to get x by itself, so now I can do that. I just need to subtract this 4 over. And then I have x equals, and remember with complex numbers, we write the real part first, the part that doesn't have the I. So I would do negative 4 first, and then plus or minus the square root of 2i next. Or sorry, not the square root of 2i, just 2i. So altogether, x equals negative 4 plus or minus 2i would be my final answer. And that cannot be simplified any further. We can't combine like the real part and the imaginary part. We just leave it as is. Okay, and then 3.3, excuse my like funky 3 in the corner, but 3.3 is complex solutions by the quadratic formula. So this was talked about in lesson 2. I think it was 2.3, if you want to go back and check that out. But the quadratic formula is x equals negative b plus or minus square root of b squared minus 4ac all over 2a. And then there is something called the discriminant, spelled like that, that kind of tells you about how many solutions you will have and what type they would be. So the discriminant is just the part of the quadratic formula that is underneath the radical. So just the b squared minus 4ac. And then, like I said over here, the discriminant tells you how many and what type of solutions a quadratic equation have. There's 3 possible outcomes. So the 3 possible outcomes come down to whether the discriminant is positive, if it's any positive number, if it's equal to 0, so if it's any positive number, if it's equal to exactly 0, or if it's any negative number. Those are the 3 possible outcomes and how it's kind of separated. So if you have a positive discriminant, that means that you have 2 real solutions. And the word real here matters. It's not just like making you write an extra word. It matters because there's going to be a case where we have non-real solutions like complex solutions, imaginary solutions. And then what that looks like on a graph is, and this is just going to be a sketch here, it's going to be a sketch 2, is 2 real solutions is related to 2 x-intercepts. So I want you to draw any quadratic, which a quadratic, remember, is a parabola, it's the U shape, that has 2 x-intercepts. It can be opening up or opening down, but it needs to cross the x-axis in 2 places. So 2 x-intercepts. And then if the discriminant is equal to exactly 0, that means there is 1 real solution. And what that looks like on a graph is it has 1 x-intercept. So basically the vertex of the quadratic or the parabola is on the x-axis. So same thing, it can be opening up or opening down. I'm going to make this one open down. But the vertex, like the point where it changes direction, is exactly on the x-axis, and that's the only point. So this one will have 1 x-intercept. And then when you have a negative discriminant, that's the last outcome. There is technically no real solutions, but there is 2 imaginary solutions. So I'm going to write both of those down. So no real solution. So no real solutions. There's 2 imaginary, or we read it as like 2 complex solutions. So 2 complex solutions. And what that looks like on a graph is that there are no x-intercepts. So it can be above the x-axis and go upward, or you can make it below and go downward, whatever you prefer. Either one works. It just can't cross the x-axis at any point. So just leave yourself a note that there's no x-intercepts. The next example says use the discriminant to determine if 3x squared plus 4x plus 22 equals 0 has complex solutions. So if we're using the discriminant, we just get to use the smaller version of the quadratic formula. So that is like the b squared minus 4ac. And then we want to figure out what our a, b, and c are. The equation that we were given is already in standard form, so we don't need to reorder it. A would be 3. B, the coefficient of x would be 4, and then c would be 22. So we just need to take each of those and substitute them in. So b was 4, so we'll do 4 squared minus 4 times A was 3 times C was 22. So A was 3, 3 went there. B was 4, 4 went there. And then C was 22, which went there. And then now we should go ahead and simplify. So 4 squared, that is 16. And then minus 4 times 3 times 22. So 12 times 22 is 264. And then 16 minus 264 is negative 248. So our discriminant is negative 248, and then the problem itself said to use the discriminant to determine if that equation has complex solutions. So we got a negative discriminant. We would go up to where it says negative discriminant up here and see what that's telling us. It's telling us it has two complex solutions. So we would say yes, two complex solutions. And then for the last part, it's just now asking us to go ahead and find those solutions. So luckily though, we've already kind of done some of the work. So to avoid, I guess, doing the same work twice, we can take the discriminant that we just found, negative 248, and we can put it where the discriminant goes in the quadratic formula. You don't have to do that. Like, you can kind of just replug in all the numbers if you want to. You should get the same answer. But just to kind of save yourself some work, the discriminant is that part underneath the radical. We already found that, so we can just take it and put it underneath the radical. So it'd be negative b, which b was 4. So negative 4, and then plus or minus the square root of b squared minus 4ac, but that's the discriminant. We already found that. We ended up with negative 248. And then over 2a, so 2 times a was 3. So since we already found the discriminant, we just had to go ahead and find b again, which was 4, so we put that in there. And then a was 3, so we put that in there. Okay, and then we'll just continue to simplify. So negative 4, and then plus or minus, for the square root of negative 248, I know it's negative and it's going to give me an I, but I do want to try to simplify that radical. So I'm going to go off to the side over here to simplify it. So for negative, or I'm not going to include the negative, we'll worry about it after. Just for 248, we just want to think of like any two factors that multiply to 48. So I see like we can divide it by 4. So if we do 248 divided by 4, it's 62. And you can do like divided by 2, like do 2 times whatever if you want to. It just has to be any two numbers that multiply to 248. And then for the 4, we can break that down into 2 and 2. For 62, it would be 2 times 31, which the 31 can't go any further. It's prime, so we're done there. And then we're looking for our pairs. And we have a pair of 2s, so I can pull out a 2. And then because it was a negative inside the radical, if I take the square root of that, I get I. And then I have a few things left over inside the radical. I have this 2 that wasn't part of a pair, and then this 31. So I would have to multiply those back together to get 62. And then that would be over the 2 times 3, so over 6. And then we just want to check to see if we can reduce this answer, kind of like the same way you would reduce a fraction. Like, for example, I would change 3/6 down to 1/2 to get a more simplified answer. I'm going to do the same thing here. So you can only do this after you simplify the radical. So now we're looking at this number, and this number. And since they're all divisible by 2, I can go ahead and reduce by 2, go ahead and divide each of those by 2. I don't change the number inside the radical. Think of that as kind of like little jail cell, so it stays the same. So the negative 4 becomes a negative 2 when I divide it by 2, and then plus or minus, this 2 divided by 2 is 1. I don't need to write the 1, I can just write I. And then the square root of 62, that stays exactly the same. And then over 6 divided by 2, so 3. So -2 plus or minus I root 62 over 3. One thing I just want to stress before the end of this is we can't simplify this before, sorry, you can't reduce your answer until after you've simplified the radical. So for example, like I know this is a 6 down here. I couldn't have reduced the 4 and the 6 because I didn't have a number in this spot in front of the radical, and I can't divide like what's inside the radical. So you just have to make sure that you, I'm going to leave a note for it, but simplify the radical first before, I guess, you reduce your answer. So simplify the radical first, that's what we did, like from here to here was step 1, and then from here to here was step 2, reducing. So just try to keep it in that same order.